this video we're going to look at solutions and solubility. In the image you can see sugar being added to water. The crystals of sugar appear to disappear in the water as they dissolve, which means the sugar is forming a solution. In this example, the sugar is the solute. And the water is the solvent. Together, the sugar and the water form a solution, and a solution is a mixture of the solute and the solvent. And this can happen because sugar is soluble in water, which means it can dissolve. What's actually happening when the sugar dissolves into the water? Well, if we could see the particles in the sugar would look something like this. And the particles of water would look something like this. Sugar is a solid, which means the particles are in a regular arrangement and they're very close together. Water is a liquid, which means the particles are also very close together, but they're in a random arrangement. The particles of water can move over and around each other, whereas the sugar particles are in fixed positions, they can only vibrate. If we take some of the sugar and add it to the water, the solution would look something like this. This shows a sugar solution. When sugar is put into water, the water molecules break the sugar into individual molecules. These molecules of sugar are then dispersed throughout the water and are so small that they cannot be seen individually. In such a state, the sugar is said to have dissolved in water. Each sugar molecule is now surrounded by water molecules. If we tried the same thing with sand and water, you would see all the sand sink and settle in the bottom of the beaker. This is because sand is insoluble in water. Insoluble means the substance can't dissolve in the solvent. If we add blue copper sulfate crystals to water, then a blue solution of copper sulfate is formed, something that looks like this. In this example, the solute would be the copper sulfate, the solvent would be the water, and together they would form a copper sulfate solution. We can say that we now have aqueous copper sulfate. Aqueous means the substance is dissolved in water. However, if you kept adding copper sulfate, you would see something that looks like this. Eventually we get to a point where no more copper sulfate will dissolve and the excess just sinks to the bottom. Excess means more than enough. We now have a saturated solution of copper sulfate. Saturated means no more of the solute will dissolve in it at that temperature. Solubility is the amount of a solute that will dissolve in 100 grams of a solvent at a given temperature. Different substances have different solubilities. The graph shows that the solubility of lithium chloride is higher than that of copper chloride, magnesium chloride, and sodium chloride, with sodium chloride having the lowest solubility. Temperature affects solubility. In the table we can see that the temperature of the water is increasing, and the mass of sodium carbonate that dissolves in grams is measured. As a graph, it would look something like this. As you can see from the graph, as the temperature of the water increases, the mass of sodium carbonate that dissolves also increases. We can show how the temperature affects the solubility of different substances by drawing a solubility curve, which is a line graph showing the relationship between temperature and the solubility of the substance. As you can see for potassium nitrate and ammonium chloride, as the temperature increases, so does the solubility. And potassium nitrate is much more soluble at higher temperatures than ammonium chloride. If we look at the solubility curves of sulfur dioxide and ammonia, we can see that as the temperature increases, the solubility actually decreases. This is because the solubility of gases decreases as the temperature increases. Let's go through some examples of questions about solubility curves. The first one is, what is the lowest temperature at which we can dissolve 35 grams of potassium chloride in 100 grams of water? Well, you would need a ruler to find where potassium chloride has a solubility of 35 grams on the y-axis, and you would draw a horizontal line to the line of best fit. Then you need to draw a vertical line from the line of best fit going down to the x-axis. Where the vertical line touches the x-axis is the temperature. So this is approximately a temperature of 24 degrees Celsius. In our next example, we need to find how much potassium nitrate will dissolve in 100 grams of water at 40 degrees Celsius. So now we need to draw a vertical line going up from the x-axis of 40 degrees Celsius to the line of best fit. Where the vertical line touches the line of best fit, we need to draw a horizontal line going across to the y-axis. Where the horizontal line touches the y-axis is our answer. So approximately 65 grams of potassium nitrate will dissolve in 100 grams of water at 40 degrees Celsius. In our next example, we need to find how much solute will dissolve in 50 grams of water at 60 degrees Celsius. So once again, let's draw the lines to and from the line of best fit. So we get a solubility of approximately 124 grams in 100 grams of water. However, we want how much solute will dissolve in 50 grams of water, so therefore we need to divide this by 2 because 50 grams goes into 100 grams twice. And we get an answer of 62 grams. So 62 grams of sodium nitrate will dissolve in 50 grams of water at 60 degrees Celsius. In our next example, we need to find the lowest temperature required to dissolve 50 grams of potassium nitrate in 200 grams of water. The solubility on the graph is in grams per 100 grams of water. 100 grams goes into 200 grams 2 times, which means we need to divide 50 grams by 2. And this gives us 25 grams. So we need to find the temperature at which potassium nitrate has a solubility of 25 grams. So we need to use our ruler to draw horizontal and vertical lines to and from the line of best fit at a solubility of 25 grams. And we get a temperature of approximately 14 degrees Celsius. So the temperature required to dissolve 50 grams of potassium nitrate in 200 grams of water, or 25 grams of potassium nitrate in 100 grams of water, is 14 degrees Celsius. For our last example, 60 grams of ammonium chloride is dissolved in 100 grams of water at 80 degrees Celsius. The solution is then cooled to 30 degrees Celsius. What mass of crystals would form? Would the solution still be saturated? So I've shown on the graph a red X to show the current mass of ammonium chloride dissolved in 100 grams of water at 80 degrees Celsius. And as you can see, the X is below the line of best fit, which means the solution is not saturated. So if we draw a horizontal line across to the y-axis, we can see where the horizontal line crosses the line of best fit. If we go down from this temperature, we can see that crystals would start forming at a temperature of approximately 70 degrees Celsius, and they're cooling it down all the way to 30 degrees Celsius. If we draw a vertical line from 30 degrees Celsius up to the line of best fit, and then a horizontal line to the y-axis from this point, we can see that at 30 degrees Celsius, ammonium chloride has a solubility of approximately 41 grams per 100 grams of water. So we started at 60 grams, and from there it cooled down to 30 degrees Celsius, and 100 grams of water at 30 degrees Celsius has a solubility of 41 grams. So if we take away 41 grams from our initial 60 grams, we get 19 grams, which means 19 grams of ammonium chloride crystals would form if the temperature was cooled down to 30 degrees Celsius. And yes, the solution would still be saturated. However, if the solution was cooled down further, more crystals would appear. Pause the video here and try these 3 practice questions. Here are the answers. Like the video if you got them all correct.